3 concrete floors are hanging over your head. Each one is 7 inches thick and roughly the size of a tennis court, and the only thing holding this corner of them up is a steel nut, resting on a steel ledge about as wide as your hand. In the next few minutes, you're going to watch that ledge tip, and you're going to see the arithmetic that says it was always going to, because the men standing under it had been asked to raise those floors by half an inch, and half an inch, at this column, needed more force than their machine was able to make. On the 23rd of April, 1987, an apartment building was going up on the edge of Bridgeport in Connecticut. The building was called L'Ambiance Plaza, 13 stories, in 2 offset towers, standing on top of a parking garage. At about 1:30 that afternoon, it was a little over half built. 3 levels of the garage were finished, and somewhere between 3 and 6 floors stood in each tower. Within seconds, all of it was on the ground. 28 construction workers were killed. It was the worst construction accident in the United States since a cooling tower came down at Willow Island, West Virginia, 9 years earlier. What made this building unusual was the way the floors got up there. In lift-slab construction, you do not pour the floors in the air. You cast every one of them on the ground, stacked one on top of another like a deck of cards. Then you thread steel columns up through holes left in them. You put a hydraulic jack on top of each column, and you lift the floors up the columns on steel rods. The argument for the method was money. Casting on the ground removes about 90% of the formwork you would otherwise need, and the report lists cost saving and speed of construction as its 2 main advantages. So, a lift slab building spends its entire construction hanging from its jacks, and that means everything depends on one small joint, repeated at every column, on every floor. Cast into each slab, wrapped around each column, is a steel collar called a shear head. In the finished building, its job is to carry the floor's weight into the column. During construction, its job is different. Welded inside it is a small steel bracket called the lifting angle. The rod that runs down from the jack passes through that bracket, and a nut threaded onto the bottom of the rod rests on the ledge of the angle. That is the whole connection. A nut sitting on a ledge with 3 floors on top of it. Floors were not lifted straight to their final height. They were raised in packages of 2 or 3 and then parked partway up while the crew got on with something else. Parking a package meant driving a steel wedge into the gap between the slab and a block welded to the column, tack welding that wedge in place, and taking the weight off the jack. At 1:30 that afternoon, a crew was doing exactly that in the West Tower. 3 slabs, floors 9, 10, and 11, were hanging on the rods, and the men were fitting the wedges underneath at a column the drawings call E4.8. Now, which column that was matters enormously. And this is where the report becomes far more interesting than the story anyone tells about it. Not every column carries the same load. The floors are flat plates, so their weight finds its way down to the supports unevenly, and the investigators built a computer model of the half-finished tower to work out exactly where it went. Their answer was this. With the slab sitting level, the jack at column E4.8 was carrying a calculated 152 kips. That is about 69 tons, and it made that column the most heavily loaded one in the West Tower. The men were fitting wedges under the heaviest corner in the building. To get a wedge in, the slab has to sit at exactly the right height. If it is a fraction low, you raise it. That is ordinary work, and it happens at every column, on every lift. So the investigators put a very simple question to their model. What would it cost in force to raise that package of 3 slabs by 1 full stroke of the jack, half an inch, from the position it had been cast in? The model returned a number, 201 kips. Then they went and established what the jack was actually able to do. Employees of the lifting subcontractor testified that while raising a package of 3 slabs, the system console normally supplied a line pressure of between 2,300 and 2,500 pounds per square inch, and that the highest pressure the system could reach at all was around 3,000. Allow 5% for friction losses, and at that column, the normal working force comes out between 137 and 149 kips. At the absolute maximum the system could produce, it comes out at 179. The job needed 201. The machine flat out could make 179. The report puts it plainly, the jack at that column would not have developed the force required for that adjustment, even when operating at the maximum possible line pressure. And that is only half of the problem. Investigators recovered shear heads, jack rods, and jacks from the landfill where the wreckage had been taken, and they loaded them in the laboratory until they failed. They ran the test 5 times over, varying how tightly the shear head was confined and how far off-center the rod pulled. The assemblies failed in one of 2 ways. Either the jack rod fractured, or the lifting nut slid off the lifting angle. Both kinds of failure were accompanied by a loud bang. From those tests, they put the weakest assembly's capacity at around 170 kips and the strongest at around 200. Now read the 2 sets of numbers next to each other. The most force the jack could possibly produce, 179, sits inside the range where the connection lets go. There is a second version of this sequence, and the report walks through that one too. If the jack at that column could not make the lift, there was a bigger one standing nearby. The jack on the neighboring column, E3.8, was rated at 300 kips, and it could have been used to make the adjustment instead. At normal line pressure, it had force to spare. But raising the package half an inch at that column develops a reaction of about 190 kips. And on the type of shear head fitted there, 190 kips produces, in the report's own phrasing, very significant rotations of the lifting angles. Whichever way you tell it, the number lands in the same place. When investigators examined the columns afterwards, they found the sequence written on the steel, about 52 inches below the top of column E4.8, on each side of the web were impact marks, the marks of lifting nuts kicking out from underneath the angles. On the lifting angles at the neighboring column, the bearing surfaces showed that kick-out had happened there as well, both columns. And once the first support was gone, the load shifted onto the others along that line, and they went in turn. Here's the part that almost never survives the retelling. The investigators did not claim they had proved it. Their finding is a most probable cause, and when they reached the decisive sentence, this is what they wrote. Whether loss of the jack at column E4.8 was the cause of the collapse, or simply one of its effects, cannot be established with certainty, and there is at least one other sequence of events that could have produced the same result. They also wrote that the actual capacity of the lifting assembly at every column in that structure will never be known exactly. The welds, incidentally, were poor. Some of them did not meet the workmanship standards of the American Welding Society. Investigators looked hard at those welds, and at the concrete, and at the ground underneath, and concluded that none of the 3 played a significant role in starting the collapse. So put the report's own scorecard on the screen. For every failure mechanism it examined, the team worked out a reserve capacity, the load that would break something, divided by the load actually sitting on it. Punching a column up through a slab scored between 4 and 23. Buckling a column outright scored between 2 and nearly 8. Losing support at the lifting assembly scored 1.1 to 1.3. That is the entire story in a single line. This building was not brought down by anything exotic. Every other way it could have failed still had margin in hand. This one had somewhere between 10 and 30%. And the routine half-inch adjustment the men were making needed more force than there was to give. Nobody was ever found responsible. In November of 1988, less than 2 years after the collapse, every claim arising out of it was settled together for $41 million through mediation by 2 judges, rather than through the courts. The settlement assigned no blame. The federal prosecutor recommended against bringing criminal charges, citing a lack of conclusive evidence. Lift-slab construction went under a moratorium until new federal safety rules arrived in 1994. So go back to where we started. A nut on a ledge the width of your hand with 3 floors resting on it, and a job to do that needed 201 from a machine that could only make 179.